here, but we're going to do the best we can with this, okay? So here's the goal for today. And if you heard me earlier, I'm going to say this again. We are basically doing your assignment right now. The only thing that you're going to have to do on your assignment is basically condense all of this onto one single page, okay? So our objective here is to create the unit circle with common angles and trig ratios. So we want to create the unit circle with common angles, which we've heard before, and trig ratios, which we kind of know what those are. So the warm-up starts off like this. It says find the missing sides of these triangles, leave the answers in simplified radical form. So that goes to the question earlier about, is it okay to write decimals? Yeah, probably not here. It's way easier to recognize them in radical form. So 30, 60, 90. Short leg over here. Somebody raise their hand and tell me what it is. Or I'll just start calling on people. Luke, thank you very much. 1/2. Very good. Okay. Jack, what's this one?
Square root 3 over 5.
Radical 3 over 2. Okay. Perfect. Now we're on a 45, 45, 90. Dane, I need you to give me one of these legs. Samara, can you help him out?
No, I completely forgot.
Crew?
Radical 2 over 2.
Radical 2 over 2. Okay. Dane, now can you give me the other leg?
Radical 2.
Radical 2 over 2. These are things that you're going to want to be able to rattle off as if they were times tables or something like that. It would be like counting by fives. You ought to be able to do the same thing. If I look at this one right here, this is also 30, 60, 90. Lydia, can you give me this one right here? Very good. This one's 1/2. Keely, can you give me this one? Nice try, Dane. Okay, radical 3 over 2. So here's what we're going to do today. We are going to make something called the unit circle. Again, it is central to all of the stuff that we learned about with trig. And here's what the definition is for the unit circle. And you'll see why it might be useful by the time we're done with this. So the unit circle is a circle centered at the origin with a radius of 1 unit. So that's why we call it the unit circle, because the radius is just 1 unit. And it's in the most convenient place possible. It's centered at the origin. So from our study of circles, we know that the only two things that are important about a circle is where is it and how big is it. This is at the origin, that's where the center is, and the radius could not be easier. The radius is just 1. Everybody good there? Okay. The unit circle is useful, so I'm going to read some of these things because these are important, because it will allow us to quickly calculate sine and cosine functions of common angles using the x and y coordinates. So we talked yesterday about how we can put that on there, reference triangles, reference angles, and direction and sine and all that sort of stuff. This is going to be extremely useful because by the time we're done, you can see that we can find all the other trig functions with just sine and cosine. That's all you need is just sine and cosine, and we'll be able to find all the other ones. Okay? Note, would you put a star by this? If you think about the unit circle, understand how the measurements are related to each other, so please make sure you're tuning in. If you're drifting off, I need your attention all day today. Okay? You'll do better in this class, on exams, and in future math courses. So if you understand this really well in the relationships, and it will take time for this to sink in, don't worry, you don't have to get it all in one day. It's going to seem like a lot to memorize and stuff like that, but if you understand how things work and recognize the patterns, it's really not a bunch of memorizing. Really all you have to know is the values in the first quadrant. If you know the first quadrant really well, Q1, everything else is going to be a piece of cake. So we're going to come down here, and here's the first part of the activity. So this is for quadrant 1. It says label the radius for each circle below is 1 unit. 1, 1, 1. Draw a reference triangle for each angle by drawing a line from the point where the radius meets the circle straight down so it meets the x-axis at a right angle. We're drawing something here. It has a name. Can somebody raise their hand and tell us what we're drawing? Thank you for raising your hand. What do we call those? Dane, let's hear it. It is a reference triangle. We just drew a reference triangle for every single one of these. Now, since Dane is on a roll, we're going to check and see how this is going. Dane, can you tell me what this is right here? What this side is? It's a trick question. I want you to tell me this one. That's 1. 30 degree. That's 1/2. Very good. Can you tell me this one? Radical 3 over 2, okay? So let's do the same thing over here, okay? On the 45, 45, 90. Sai, you weren't here yesterday. Can you help me out on this one?
I have no idea.
Good. We're going to call on Megan. Megan, can you help us out with the 45, 45, 90? We've got 1 for a hypotenuse. How long is this side?
Radical 2 over 2.
Radical 2 over 2. And can you tell me this one?
Radical 2 over 2.
Radical 2 over 2. Okay? Wilson, can you help me out with this one right here?
That's 1/2.
That is 1/2. Everything on a 30, 60, 90 goes through the short leg. And Samara, can you tell me what this one is? Radical 3 over 2. Now, it says, use what you know about special right triangles to find the x and y coordinates so you can label the point where the radius meets the circle. Do this for each one of them. So we've kind of done each part of this, but we've left something off. This point right here actually is a coordinate on the xy plane if this is in quadrant 1. So can somebody raise their hand and tell us what's the x coordinate here? Thank you, Jack.
1, 1.
Ooh, not right here.
Oh,
That's 1 unit long. How far would we go to the right and how far would we go up?
go 3 square or radical 3 over 2.
Radical 3 over 2, comma,
1/2.
1/2. Everybody good with that? Okay, Gavin, tell me what this one is. What's the x coordinate here?
Radical 2 over 2.
Comma,
Radical 2 over 2.
radical 2 over 2. Angela Dewey, can you do this one for me?
1/2 and radical 3 over 2.
Okay, everybody okay with that? Okay, now, here's where it gets kind of interesting. I want to figure out the cosine of 30 degrees. So this is a 30-degree angle, correct? I want to figure out the cosine. Hannah, what sides are involved in the cosine ratio? The adjacent and the hypotenuse. So it's going to be the adjacent, which is radical 3 over 2, divided by the hypotenuse, which is 1. So what's the cosine?
Radical 3 over 2.
Radical 3 over 2. I want to find the sine of 30 degrees. So Lydia, what two sides are involved in the sine ratio?
Opposite and hypotenuse.
Okay, so the opposite side is 1/2 and the hypotenuse is 1. So if I simplify that, Keely, what do I get? I get 1/2. Okay, perfect. I got the cosine of 30 and I've got the sine of 30. Let's come to the next one. Lydia, what two sides are involved in the cosine ratio? Okay, so what's the adjacent on the 45 here? And what's the hypotenuse? 1. Okay, so can you tell me what the cosine of 45 is? Radical 2 over 2. I've got that one. Okay, Andy, what two sides are involved in the sine ratio?
Opposite and hypotenuse.
Can you tell me what the opposite side is here?
Radical 2 over 2.
And can you tell me what the hypotenuse is?
1.
Perfect. Can you tell me what the sine of 45 is then?
Radical 2 over 2.
Radical 2 over 2. Okay, would you take just a second and finish those? I want you to find the cosine of 60 degrees and I want you to find the sine of 60 degrees. Now, we're going to see how Sai's doing here because he wasn't here yesterday, so he's a little behind the curve on this one, but I think Sai can get this one. Sai, can you tell me what the cosine of 60 degrees would be? It is 1/2. So I'm just going to put a 1/2 here. Is everybody okay with that? Because isn't it kind of silly to divide by a hypotenuse of 1? Okay, perfect. Okay, can you tell me what the sine of 60 degrees is? Radical 3 over 2. Okay, so everybody good with that? Okay. The next question is, what do you notice about the coordinates you found in part C up here and the trig ratios you found in part D? Now, Luke has his hand up. I don't know if it's the answer to this question or something else. Is it the answer to this question? Hang on. That's a simple one. Just tell me, is it the answer to the question I just asked?
I don't think so.
Okay, hang on. Colson. Here, hold on. Let me restate the question so everybody's clear on what we're doing. The question is, do you notice anything about the coordinates, the xy coordinates up here, and the answers that we got right here? Go ahead.
The x-coordinate is the same as the cosine, and the y-coordinate is the same as the sine.
Okay, that's the conjecture. That's the guess. Okay? So he actually went from here down to here. He actually answered the next question. Did you read the next question?
No.
Sweet, this worked really well. Okay, all I was looking for on here is, hey, wait a minute. Radical 3 over 2, radical 3 over 2, 1/2, 1/2, radical 2 over 2, radical 2 over 2. Hey, these are the same, there's got to be some relationship. Well, this is the relationship. The relationship is that the x is equal to the cosine of theta and the y is equal to the sine of theta. So there is our guess. And then I'm going to shrink this down here, and I've got a question for you. Do you think this works for 0 degrees, and do you think it works for 90 degrees? If you just had to guess.
No.
Dane says no. Crew says yes. Okay, everybody watch.
Yeah.
Okay, so I'm going to circle a yes here because we like it when Dane's wrong, right? I mean, let's just not lie about that. Okay, take a look here. I'm going to put, okay, take a look. I'm going to draw a little reference triangle for 0 degrees. So let me see if I can do this here. For 0 degrees, it would look something like this. So we've got something like that and like this. So this would be 1, and if it was truly 0 degrees, that would be 0 and that would be 1. You agree? Because we wouldn't be opening up the circle, opening up the angle at all. It would be like this. The adjacent side would be 0. Sorry, the adjacent side would be 1. The hypotenuse would be 1, and the opposite side would be 0. So that would mean that the, let's see, the coordinates of that point are 1, 0. Is the cosine of 90 degrees, is it 1? And is the sine of 90 degrees, is it 0? So would you grab your calculator really quickly?
They both are. I got those thingy because.
Oh, we got the little trig table, don't we? Okay, I'm going to pull it up on the calculator. We're just going to double check. So I'm going to type in the cosine of 0 degrees, and we get 1. And we do the sine of 0 degrees, and we get 0. So does it work?
Yes.
Okay, so on this right here, we could put 1, 0. That would be the cosine of 0. And up here, if I draw an exaggerated triangle, it would look like this. Watch. It has to be with the x-axis, so I would draw it like this. Straight up 1 unit, straight down 1 unit, and if this was truly 90 degrees, that would have to be 0, correct?
Yeah.
So the coordinates there would be 0, 1, and if you want to double check on your calculator, do the cosine of 90 right now. Or look on your little trig table. Is it 0? Cosine of 90 is 0. Sine of 90 is 1. Does it work?
Are cosine and sine
'Kay.
just like the inverses of each other?
They're phase shifts of one another and a couple of other things. Okay. Do you think it works in other quadrants also? You better think so. So flip the page over.
Probably not. I don't like this.
You'll be fine.
Do
Okay, watch. This is the cosine of theta, and this is the sine of theta. So this is how we make the unit circle. Now notice on the diagram, notice that 1 is the radius. We've got an x-coordinate, and we've got a y-coordinate, and we've got an angle of theta. So there's our angle of theta as we turn this around the entire circle. So we're going to run through here and keep this in mind. So I'm going to shrink this down just a tad. Part of this should look ridiculously familiar. So I'm going to go through and I'm going to label some of these. This would be 0 degrees, also 0 radians. If we go all the way around, 360 degrees. Somebody raise their hand and tell me what it is in radians. Thank you, Mason. 2 pi. This would be 90 degrees. Radians? What is it? Pi halves. Because over here, this is pi radians, or 180 degrees. Down here, this is 270 degrees, or can somebody raise their hand and help us out here? Dane. 3 pi halves. Very good. Now, I'm going to color code these like we did before. So, this is 30 degrees, pi 6. This is 150 degrees. Help me out. Subtract pi 6 from pi.
5 pi 6.
Thank you very much. 5 pi 6. This is 210 degrees because I'm adding 30 degrees here.
7 pi 6.
7 pi 6. So I'm going to jump over here. This is 330 degrees. 11 pi 6. Everybody good there?
Yes.
Okay. Here we go with the angles that are blue. These are multiples of 45. So 45 degrees, pi fourths.
Dang it, I was there.
135 degrees,
3 pi 4.
3 pi fourths. Tell me the degrees. 225. The radians? 5 pi fourths. And over here, Crew's arm just came out of his socket. Crew, the degrees?
7 pi 4.
Oh, okay,
Oh,
7,
that was wrong.
7 pi fourths. 7 pi fourths. What about the degrees?
315.
315 degrees. Now I'm going to do the green one.
He asked you the degrees first.
60 degrees. Samara, can I put you on the spot for 60 degrees?
I'm not gonna remember.
Pi 6.
Oh, was it pi third?
It is pi thirds. Very good. Pi thirds. Pi 6, pi fourths, pi thirds, and then we're at pi halves. 120 degrees. Crew. 2 pi thirds. Then we'll come down here. Let's see, it's 1 pi third, 2 pi thirds, 3 pi thirds. Hannah? 4 pi thirds. 4 pi thirds. That is 240 degrees.
Yes.
And then over here we get to 300 degrees, and this would be, it's got to be pi thirds, something. 1 pi thirds, 2 pi thirds, 3 pi thirds, 4 pi thirds, 5 pi thirds. Okay, everybody good there? All right, let's take a look. Coordinates. 1 comma 0,
Yes.
0 comma 1, negative 1 comma 0, 0 comma negative 1, and then we're all the way around full circle. Let's do the red ones. 30-degree reference triangle. Hey, wait a minute. We know what this one is. This one is radical 3 over 2, comma what?
1 over 2.
You got that first page showing, right?
Oh, no, because it's on the back.
Oh, okay. You can flip back and forth. Okay, what's the next one?
Radical 2.
Radical 2 over 2. Radical 2 over 2. And then what's 60 degrees?
The opposite of the red one.
It's the opposite of the red one. It's the opposite of 30 degrees. Ryan, will you pull the door shut there, please? So this is going to be 1/2, comma, radical 3 over 2. Now, listen up. Said once you have this in the first quadrant, we should see some symmetry here. If I were to take this red one, let's do the red ones here. If I take this red one and swing it over here, what's the only thing that's going to change?
A negative.
Negative on what?
The first x.
Negative on the x coordinates. So this is going to be negative radical 3 over 2, 1/2.
Yes.
If I do the blue one and swing it over here, negative radical 2 over 2, radical 2 over 2. And if I do the one for 60 degrees and swing it over here, this would be negative 1/2, radical 3 over 2. Everybody good there? Okay, what's going to happen if I take this and I swing this down here? They're both going to be negative. So this is going to be negative radical 3 over 2, comma, negative 1/2. Would you pause for just 1 second right here? Everybody pause, look up here. Negative radical 3 over 2 in size and absolute value is bigger than 1/2. Because this is a small reference angle, we're going to go further to the left than we do going down. Okay? If this is a 45-degree reference angle, we're going exactly the same amount in each direction. So this is going to be negative radical 2 over 2, negative radical 2 over 2. This one's going to be negative 1/2, negative radical 3 over 2. And then we swing back over here and we say, well, gosh, I know these now. It's the same thing, but now I'm going to have positive x coordinates. So this is going to be 1/2, negative radical 3 over 2. Tell me if I'm going too fast. We kind of get the patterns.
Yeah.
Radical 2 over 2, negative radical 2 over 2. And the last one is radical 3 over 2, negative 1/2. Okay, we good?
Yes.
Okay.
Yeah, you are.
Any questions? All right. Would you take a look at this? And keeping in mind that x is the cosine of theta and y is the sine of theta, can you tell me in quadrant 1 which ones are going to be positive, sine or cosine? Or both?
Sine is a line.
Both, because they've got positive coordinates, right?
Yeah.
So we're going to put both. Which one's positive in quadrant 2?
Sine.
Sine is, because we're looking for the y coordinate. The y coordinate's positive, so the sine is going to be positive. The cosine's going to be negative. What about in quadrant 3?
No.
Neither.
They're both negative, so we're going to put neither. Okay, in quadrant 4? Okay, the cosine of theta is going to be positive. Everybody good there?
Because.
Okay, flip the page over. Okay, now, part 1 and part 2. Let's see, I need to take a picture of this. So I'm going to grab a tool here. Now, you've got the advantage of having
A
a paper you can flip over. I do not have that advantage, so I'm going to take this and I'm going to paste this in here and slide it around so I can look at it. Everybody good? Okay, so next thing we want to figure out. Use the sides of the reference triangle that you drew in part 1, so that's these guys right here, to figure out the tangent of 30 degrees. Okay? Samara, what two sides are involved in the tangent ratio?
Opposite and adjacent.
Opposite over adjacent. So I'm going to take the opposite and I'm going to put it over the adjacent. The opposite is 1/2. The adjacent is radical 3 over 2. And I'm going to take that and I'm going to flip it over. I'm going to do the reciprocal here. So this is 2 over radical 3. Those are going to cancel, so I have 1 over radical 3. You have to do the thing. What's the thing? It's the funky looking one. We're rationalizing the denominators. So, everybody agree radical 3 over 3?
Yeah.
Okay. Tangent 45. Opposite? Hey, wait just a second.
No.
Mason? 1. Tangent 60 degrees. That's going to be the opposite. Radical 3 over 2 divided by the adjacent, which is 1/2. We're going to flip that over. Those are going to cancel. Radical 3. Everybody good there?
Yes.
I'm going to give you a second to stare at that for a minute. Are we right?
Yes.
Do you want to double check on your calculator? You want to throw it in? You want to look at the trig table?
What is tangent? Is it cosine and sine and
Hang on. Okay, now, here's what I want you to do. Now we're going to take, remember, we know, because we saw this on the last one, that this is the cosine of theta and this is the sine of theta. So if I take the sine of 30 degrees, the sine of 30 degrees is the opposite, which is 1/2. The cosine of 30 degrees is the adjacent, which is radical 3 over 2. Isn't that exactly the same thing?
Yes.
Hold on. Let's do it on the next one. Sine of 45 degrees, radical 2 over 2. Because the sine's right here, right? Over the cosine of 45 degrees, radical 2 over 2. Don't we get 1 there?
Yeah.
Don't we get radical 3 over 3 here? And guess what would happen if we took the opposite? Radical 3 over 2 over the cosine. Sorry, sine of oh, this should be 60 degrees, shouldn't it? Sorry about that. Okay, typo. That should be 60 degrees. That should be 60 degrees. So, 60 degrees, the sine is radical 3 over 2. Cosine of 60 degrees is 1/2. Aren't these exactly the same thing?
Yes.
So, does somebody want to make a conjecture about the relationship between sine, cosine, and tangent? Don't say anything. If you want to say something, you got to raise your hand. Keely.
Just like a guess, but could it be because we just found out that sine and cosine are like x and y are like opposite and adjacent, and
Mhm.
opposite and adjacent are just what goes in the tangent?
Okay, So can you tell me tangent would be, what do we put on the top?
Opposite.
What is it?
Opposite.
Opposite. So we could put opposite. And on the bottom?
Adjacent.
Adjacent. So you're right about that. Can you give me another name for this on the unit circle?
X and Y.
X and Y. Okay, so we're gonna, the opposite side is the Y and the adjacent is the X. Let's keep going with that. We know what the X coordinate is and what the Y coordinate is. What's the X coordinate? Other one. Cosine. So we're gonna put cosine here, and what goes on the top?
Sine.
Or sin, as you like to say. So here's the deal.
Wait, I said it. Wait.
Oh, you said it right? I'm sorry. I apologize. So everybody take a look at this.
He's like, shoot.
Okay. So here's our guess. Our guess is that tangent is equal to the sine of theta over cosine of theta. And remember I said at the beginning, we're going to be able to figure out every single trig function using just sine and cosine. Okay? So this is it. There's the identity. Now, we're not going to take a whole bunch of time to do this, but I do want you to notice, if we're in quadrant 1, both of them, whoops, let me put Q1.
Plus.
This is going to be plus plus. So that means the tangent is going to be positive. Over here it's going to be negative, positive. What's the tangent going to be?
Negative.
It's going to be negative. Over here it's going to be negative comma negative. What's the tangent going to be? Positive. And over here it's going to be plus comma negative. What's the tangent going to be? It's going to be negative. So the tangent is going to be positive in quadrant 1 and positive in quadrant 3, negative elsewhere. Okay? All right, so here's a mnemonic device. All students take calculus. So here's how this works. In Q1, they're all positive. In Q2, S stands for sine. Sine and its reciprocal cosecant are positive. In Q3, T stands for tangent. And in Q4, the C stands for cosine. So they're all positive over here. The sine is positive over here. The tangent is positive over here. And the cosine is positive over here. So all students take calculus. Any questions?
I don't like that.
Okay. Well, I apologize.
You like Sokoto
Okay.
more?
These are going to be helpful in a couple of days, so we're going to run through this part 4 really quickly. These are basic trig identities. So remember, a trig identity or an identity of any type is a true equation. So you're kind of already familiar with these. The reason we call these the reciprocal identities is because to get the cosecant, it's the reciprocal of the sine. So cosecant of theta is 1 over the sine of theta. The secant of theta is 1 over the cosine of theta. Remember, those are related. And the cotangent of theta is 1 over the tangent of theta. And then, of course, the opposite is also true. The sine is 1 over the cosecant of theta. The cosine is 1 over the secant of theta. And the tangent is 1 over the cotangent of theta. All this is saying is if you want one, you flip the other one over. You do the reciprocal of the other one. Okay? What we just figured out up above was this. Okay, this is what Keeley said. Tangent is the sine of theta over the cosine of theta. So do not say anything out loud. I'm going to call on somebody. If the tangent is sine of theta over cosine theta, can somebody tell us what cotangent is in terms of sine and cosine? Ooh, got some hands up. Caleb, what do you think?
The cosine of theta over the sine.
Yeah, you just take it and you flip it over. These are reciprocals of each other, so there you go. Okay, any questions? Okay, flip the page over. We're on the last page. Okay, like I said before, this takes a lot of thinking to put all this stuff together. This is a mountain of information. So here's what I want you to do. I want you to take a look at that diagram there. Here's the question. We got about 8 minutes left. I need you tuning in. If you're tuned out, I need you tuning back in. Would you look at that diagram here? Notice that this is a unit circle. Cosine is the x-coordinate. Sine is the y-coordinate. Here's our angle theta. Look at this purple line right here. Somebody want to take a look at that and say, I think I know what they might have called that. What do you think?
Line of tangency.
Ooh, very good. It is a line of tangency, so we're just going to say, hey, that's just a tangent.
No way.
That's going to be the tangent of theta. There's a couple ways that you can tell that. One, it touches at a point of tangency like Keely was saying. The other thing is, take a look. If a line meets a radius at a right angle, it's got to be a tangent. So that's what we call the tangent. So hold on. I'm going to show you one more thing here, and then we'll wrap this up. I'm going to draw this small triangle like this. This is 1. This is the this is the cosine of theta. And this is the sine of theta. Now, I'm going to take this big triangle here, and I'm going to draw it exactly the same way. So this is a right angle, and this is theta. This is still theta. How long is this? I took that and I flipped it around here. Crew.
1.
It's 1. There's the right angle. How long is this? Tangent of theta. Now, using proportions, these are two, they've got two angles that are the same. Angle-angle similarity, here's what I can write down. I can write down that the sine of theta over the cosine of theta is equal to the tangent of theta over 1. Do I need to put the 1? I don't. So here's a geometric proof of what we just did right there. Let that sink in for just a second. Oh, I don't like this.
Wait,
Okay.
There's too much.
where's the right angle?
Like I thought you were just locking this.
See the
in.
right angle there?
Like in
I
the
flipped it around.
way of.
Sorry.
Okay, hold on. We got just enough time to finish. And remember, this is your assignment. We're doing your assignment right now. Okay? I'm going to hand you a piece of paper that basically allows you to reproduce all of this on one piece of paper. Okay? That's all you have to do. So, part C. If the reference triangle is always a right triangle made with the x-axis, and on the unit circle, the horizontal leg is the cosine and the vertical leg is the sine. So that's just saying, hey, the picture looks like this little right triangle inside the unit circle there. Can you use the Pythagorean theorem to derive the most fundamental of all trig ratios? Now, trig identities. Do not say anything. I'm going to draw a picture here, and I want somebody to come up with the answer. It says use the Pythagorean theorem. Luke's got his hand up. Don't say anything. Mason's got his hand up. Keely's got her hand up. Okay, Luke, you had your hand up. What do you want to say?
Sine squared plus cosine squared equals 1.
Sine theta squared plus cosine theta squared equals 1 squared. Everybody good with that? Leg squared plus leg squared equals hypotenuse squared, right? Here's how we write it. We write trig functions when we square them or raise them to a power like this. So I'm going to write sine squared theta plus cosine squared theta equals 1. Would you put a box around that? That is the most fundamental of all trig identities. Yeah.
I was gonna say, don't you not need to like put parentheses around it because it's one number?
Whoops, I just erased that, didn't I?
Actually, like,
Whoops.
You said it's like sin.
It is one quantity, but to make it clear so nobody would mistake and say, oh, you want me to find the sine of theta squared? Okay, we usually put it like this, and then we put it here. We're squaring the value of the trig function, not the angle. Good question, though. Mason?
Is this like the hyperbolic?
No. No. Okay? All right. Last two things. Last two things, promise. What would happen if I took this? Sine squared theta plus cosine squared theta and divided both sides by cosine squared. Don't say anything. This is what we're doing. We're dividing by cosine squared.
great. Oh, you can.
Oh, don't say anything.
What? Is this beginning?
We'll do the easy part. What's this?
Nothing.
1. Don't say anything. What's this? Keely. Tangent what? Tangent squared theta. What's the last one? What is it? Very good. Secant squared theta. Okay? All right, now, here's what I'm going to leave you with. Here's what I'm going to leave you with. The last, hold on. What I want you to do is start over with sine squared theta plus cosine squared theta. So write this down. And then what do the instructions say?
By both sides, by sin.
I'm sorry, what did you say?
I went back to my ways because you bullied me for saying it
I bullied you for
correctly.
saying it incorrectly.
No, I said it right.
Oh, for saying it right? Okay, Wilson, will you tell us what the right way to do this? We're going to divide by
Sine
squared theta.
squared.
Okay, so now, this is all you have to do. We have all the answers. The only one that I didn't give you is this one right here. So you finish this one right here. It's the last one on the page. Everybody got it?
I already know
Well,
what it is.
you fill all these in, and you find this one, and then you can fill in the last one. Okay? All right. Have a great day.